So, hello everybody. We will still wait a little bit so that the participants who have followed the previous presentation can also register to this presentation. So I think we will just start in 2 minutes. 2 minutes, this means if you take my watch as reference at 55. So let's get started. Welcome to the presentation of the JMAG and PowerSys academical partner, the Technical University of Darmstadt. It will be a presentation elaborated by Robin Köstner and Dr. Björn Deusinger. My name is Martin Michels, and I'm responsible for the Frankfurt office of the PowerSys company. The subject today is export of unprocessed JMAG field solution data for custom post-processing visualization. The presentation will be a recording from Robin Köstner, and which lasts about 30 minutes. And after this presentation, Dr. Deusinger is available to answer your questions. And please put your question in the chat from Zoom or the answer questions and answer section. So, regarding the two presenters, firstly, yes, Robin Köstner. So he was born in 1993 near Frankfurt in Germany. He has received his Master of Science in Electrical Engineering in 2018 and his Master of Science in Condensed Matter Physics from Technical University of Darmstadt in 2020. Since 2019, he is with the Institute of Electrical Energy Conversion at the TU Darmstadt as a research assistant. His field of research are electrical machines, especially direct drive synchronous machines for wind turbines and superconducting rotating machines. Dr. Björn Deusinger was born in 1986 in Frankfurt, Germany. He received his diploma degree in electrical engineering in 2013 and his doctoral degree in 2020 from TU Darmstadt. Since 2013, he is with the Institute of Electrical Energy Conversion at the TU Darmstadt as a research assistant. His research interests are electrical machine design of traction and industry drives and efficiency determination of electrical machines. So the recording which you will hear will be from Robin Köster, and after this recording, Dr. Deusinger will be available to answer your questions. So I will start the recording now.
Welcome to my talk on script-based solutions for simulations with JMAG, in which I want to discuss the export of unprocessed data and subsequent post-processing as a first part. And the second part of the talk, which is not properly covered by the title, is a script-based simulation of superconductor properties, which might also be interesting at this point. My name is Robin Köster, and I'm with the Institute of Electrical Energy Conversion at Technical University Darmstadt, headed by Professor Andreas Binder. And our contribution today comprises my talk, and related questions are thereafter answered by Mr. Deusinger. At the right-hand side, you can see a stack of high-temperature superconducting tapes in a JMAG model which carries AC current, and the contour plot shows the current density, where you can clearly observe the current penetration front in the stack, and this model is also discussed later in this talk. So let me first give an overview of the content of this presentation. I will start with a short introduction from an application-oriented perspective, followed by the section on the export of unprocessed field data. The third section is, as already mentioned, on the script-based simulation of superconductors with JMAG 20, and the talk closes with a short summary. We are using JMAG for the simulation of rotating electrical machines with superconducting winding and the special material properties of particularly high temperature superconductors require some additional steps that are usually not part of the standard procedure for the analysis of rotating machines. And for these steps, script-based solutions help to integrate JMAG computations into automized calculations. High-temperature superconducting windings generally have potential for weight-critical applications, as we can reach much higher magnetic fields and higher current densities in case of both DC and AC current. And the first prominent example consists in wind turbine generators, as shown as an example on the right, with flux lines for nominal operation. And a second example are superconducting machines for more electric aircrafts, which is a research field with several large-scale projects that are recently carried out both by universities and leading companies in the aircraft industry. In general, both excitation windings, as in the example on the right, and the stator winding can be made from superconducting winding tapes, so that the superconductor may be subject to either DC or AC current and always experiences a DC magnetic field as well as an additional AC field. So what is special about superconductors in numerical modeling? There are two key characteristics which are quite difficult to model. First, the critical current of the superconductor must be covered, which is the maximum current carrying capacity of the superconductor before leaving the superconducting phase. And this quantity depends on the temperature and the local magnetic field, as shown in the figure on the left. And in the latter case, the strongly anisotropic behavior of so-called coded conductors, for example IPCO, leads to a dependence of both the absolute value and the orientation of the field. And still, an even more advanced treatment would also incorporate a stress dependence of the critical current. And at this point, it is desirable to have access to field data in the entire winding window. So here, essentially, in order to ensure that the maximum current limitations are kept. The second characteristic which is challenging to model is the AC loss in the superconducting winding. So-called hard superconductors allow for nearly loss-free transport of DC current, but they experience some AC loss if they are facing AC current or an external AC magnetic field. And these losses are a highly nonlinear function of the applied current amplitude and are at a microscopic level associated with the movement of flux vortices, and within an effective description they are associated with the flux penetration into the superconductor. And since the direct simulation of superconductors is quite time-consuming, an efficient way to estimate the AC loss is to simulate the rotating machine with a uniform current density in the winding window and a subsequent application of analytical AC loss formulas. And these AC loss formulas or analytical models require detailed information about the local current carrying capacity and about the local AC field, and both can be determined by exporting the field data from JMAG. The alternative way, as already mentioned, consists in a direct modeling of the HDS properties by, for example, power law relations, which can also be assigned in JMAG. But here, the assignment of the material properties is not possible by means of the JMAG designer, but requires a direct manipulation of the JCF file, which has to be carried out for each superconducting part individually. And in case of many parts, for example, if each turn of a superconducting winding stack has to be modeled, a script-based solution helps to set up these models, as we will see later in this talk. And before showing our application examples, I would like to mention that the script-based solutions can mostly be implemented in both MATLAB and Python, and we therefore switch depending on the individual application and also within this talk. In the next section, I want to give an example for the use of exported field solution data from JMAG. And to get an idea of the general workflow, I want to shortly describe the use of the JeneralInterface application. The export of mesh information and the complete set of field solution data is not possible by means of the JMAG designer, but quite easy with this application. The executable is located in the JMAG installation folder, and on the right-hand side you can see the user interface. There are several settings that determine, amongst others, the file format of the export, the exported data, and the considered frames in case of transient analysis. And there is an option to include mesh information during export, which allows to determine the associated mesh element for an arbitrary point within the simulation domain. And instead of selecting manually, you can also use an XML file to automatically set up the export, and this is what we do in our studies. We use a template XML file which is completed by means of MATLAB code, and an excerpt of an example is shown in the middle here, which just requires to replace the spaces by the respective part ID. These part IDs can either be manually determined by means of the JMAG designer or are more suitably already available from a script-based build-up of the model. At the bottom of the slide you can see the example MATLAB code for the export, which in this case used JMAG 19 and where the path to the preconditioned XML file is just transferred as an additional parameter. In this example, several CSV files are generated for each part under consideration, and each of these files contains the magnetic field data for all selected frames. The next step is now, or consists in reading the CSV files to data matrices, where here we give a MATLAB example, even though Python would work just as well. And the CSV file contains three main sections. First, the information on the mesh nodes, that is the node ID and its position in units according to the export settings. And here, for example, we have a direct drive wind turbine generator with a quite large radius of around 3000 millimeters. The second section contains the information about the mesh elements, where here we have triangular elements and each row corresponds to one element and contains the node IDs of the belonging nodes which span the bounding edges. And the third section finally contains the field data, in this case the X and Y component framed in red, and the element ID so that all information for subsequent steps is available. On the left-hand side, you can see an example of one rotor pole of a direct drive wind turbine generator with HTS excitation winding and an enlarged section of a single HTS tape with a substrate and a stabilizer and a very narrow superconducting layer in between. This geometry poses some challenges, as we will see later in this talk, and therefore a first way to characterize the winding consists in applying a kind of mean field approach. That is, we discretize the winding window in space to grid, as shown on the right, and we ask for the properties in each grid point and assign these properties to the respective volume element. And here we could also use a quadrilateral region mesh, but this does not change the results significantly. In principle, we have all the information to characterize each grid point based on the exported data, but we have to determine which element the grid point belongs to. And this task can be computationally expensive, but is well manageable by means of a vectorized implementation. And after discussing the method, I would like to show some results for the estimation of the AC loss. We consider again the HTS excitation winding for the direct drive wind turbine generator, which is simulated in a transient analysis with JMAG 20. And this excitation winding is, despite of an electromagnetic damper screen, subject to some residual air gap field harmonics. The first step consists in determining the critical current for each grid point, which is assumed to be a function of the time averaged magnetic field. And we consider a uniform current density in the entire winding window, and the ratio between the transport current and the critical current is shown in the figure on the right. The upper right corner of the winding window is next to the pole surface of the ferromagnetic pole and therefore experiences the largest rotor field, and this field reduces the current carrying capacity so that even in case of a uniform current density, the ratio of transport and critical current varies gradually among the grid points in the winding window. And when it comes to AC loss, which is shown in the figure on the left, the AC magnetic field in the respective point is also very important. The course of the local magnetic field over time is available from the export and transformed to the frequency domain by means of a fast Fourier transform. So we have the pointwise spectrum of each component of the flux density available and use this as input for an analytical loss model. The results of the volumetric loss density are color encoded, and we can observe that the AC loss density is particularly high if either the critical current is low or the AC field is high, which is the case for the lower right corner with minimum distance to the stator. So this was the example for an automized export of unprocessed data, and now I would like to switch to the direct implementation of superconductor properties with JMAG. And as brief introduction, I would like to shortly discuss the main characteristics. So we consider so-called hard superconductors, where pinning forces prevent flux vortices from moving freely inside the superconductor. And in this case, we would expect a zero resistance for DC currents as long as we stay below the critical current. For the field numerical implementation, we have to specify a local relation between the electric field strength and the current density, as shown in the figure, where the dotted line corresponds to a bean model, which exactly shows the aforementioned properties, that is, zero loss below some critical current density and a jump to very high values as soon as the superconducting phase is left. However, in practice, there are effects such as thermally activated flux motion, which lead to some finite loss dissipation even below the critical current density. And this behavior can be described by a power law, as shown here. The critical electric field strength is usually defined as 10 to the power of -4, and the exponent n is typically in the range from 20 to 30. And this relation is continuous and differentiable and can therefore directly be introduced into the field numerical problems. The figure on the left shows some power laws for different exponents, where we can observe that the relation converges to the Bean model or the Bean critical state model as n increases. This can also be shown in a mathematically thorough way, which was done by Barrett and Prigogine. And it should be mentioned that the critical current density is in general, of course, also a function of the local magnetic field and temperature. JMAG allows to define superconductor properties in several ways, including the Bean model, a power law relation with or without field-dependent JC, and even custom models that can be incorporated by individual DLLs. However, these models cannot be applied by means of the JMAG designer, as already said, but rather by directly manipulating a previously exported JCF file. For example, by means of a pre-implemented Excel and Visual Basic for application solution. An example for such an Excel sheet can be found in the JMAG installation directory, and we use a customized version of this VBA code for assigning material properties. The VBA code has to be executed for every part individually, and here one can strongly profit from a script-based solution. An example for an implementation with Python is shown on the right, where we just automatically fill the respective parameters and then iteratively apply the settings to all superconducting parts, where again the part IDs must be available, for example, from the script-based model buildup. And in the following, I would like to show you some additional challenges and results that relate to the simulation of superconductors in JMAG. And for all these studies, as an example, we assume a tape with the characteristics shown on the right here. That is a 4.35 millimeter wide tape with a thickness of 0.2 millimeters, a superconducting layer thickness of 2 microns, which can carry 100 amps in the cell field at liquid nitrogen temperature. So, which parameters must be specified in JMAG? First, we can choose the model to apply. That is a Bean model, a power law, or a custom relation. In the following, I will just focus on the power law, since this model shows comparably good convergence and has proven to produce experimental data quite accurately. And in this case, we have to define the critical current density and the exponent, which both depend on the individual tape and which are suitably taken from manufacturer's data or from experiment. And in addition, we have to define the critical field strength, which in JMAG is done implicitly by specifying the so-called initial conductivity. And an important feature of the power law settings in JMAG is the introduction of a maximum effective conductivity. This can be seen in the figure on the right, where the conductivity is plotted at a logarithmic scale versus the current density for several exponents. And we observe that the conductivity increases to extremely high values for large exponents n towards low current densities. And here the truncation of the relation at a certain maximum conductivity improves the numerical stability. But we can observe that the deviation from the power law is especially pronounced for high exponents n. And a corresponding study reveals that particularly the computed AC loss is quite strongly affected if the maximum conductivity is chosen too small in relation to the critical conductivity, so that at least 3 orders of magnitude should lie between these quantities. And in addition, JMAG directly allows to specify the field dependence by means of the pre-implemented VBA code. And on the right-hand side, you can see again an exemplary Python implementation where we just automatically fill in the Excel sheet before executing the respective macro. Before running the simulation in JMAG, we have to make sure to specify suitable solver settings in the study properties, that is, amongst others, a quite low tolerance and high number of iterations. And we have to consider that a high exponent n generally implies a much slower convergence of the highly nonlinear problem. So to summarize this workflow, the first step is the creation of the geometry and the specification of general settings as for conventional models. Then we have to specify the mesh, which is quite important for this highly nonlinear problem and which is the content of the next slide. This is followed by the export of the JCF file, which is then manipulated by means of the VBA code, and the final step is the submission to the scheduler, which must be done directly without opening the modified JCF file with the JMAG designer. The strong nonlinear behavior of the superconductor is one challenge, but another severe difficulty arises from the very high aspect ratio in case of coated conductors. On the right-hand side, you can see the architecture of a typical tape, in this case from a German manufacturer, Teva. And these tapes typically have a width of 4 or 12 millimeters, whereas the superconductor or the superconducting region's thickness is just in the order of a few microns. And this situation makes the choice of suitable mesh quite difficult, as can be seen on the left. The lowest strip corresponds to a to-scale modeling of the superconducting layer, where we cannot even see the individual mesh elements. And in the following, I will focus on quadrilateral mesh elements, which can be set by means of a region mesh in the JMAG geometry editor, and which have proven suitable for this type of problem. So a to-scale model of the superconductor would lead to an enormously high number of mesh elements and an impractically long simulation time. And the common way to circumvent this difficulty consists in an increase of the tape thickness by reducing the critical current density in order to maintain the same current carrying capacity of the tape. This is known as the artificial expansion technique in literature and is visualized in the figure or in the upper figure on the left. This approximation is justified by the fact that the current as well as the field penetrates the tape starting from the outer edges, so that the behavior of the superconductor is approximately a one-dimensional problem. However, the artificial expansion leads to some deviations in the estimated AC loss, as can be seen in the figure on the right, where we plot the loss power versus the tape thickness by normalizing to the value of the to-scale model. And here we can observe that the differences increase towards lower current loadings of the tape, which are however not of practical importance. In case of a good utilization of the tape, that is ratios in the order of 0.75, the inaccuracy is quite low, up to values that are one order of magnitude larger than the actual thickness of the superconducting layer. And we therefore use a tape model with thickness of 20 microns for the following illustrations. And to get a better idea what happens in the superconducting tape, we'll look at a situation where the introduced tape with an IC value of 100 amps is loaded by an AC current with an amplitude of 74 amps. The course of the current is visualized in the upper figure on the left, and you can see the current density profile on the right for several time instants. The choice of the time step of the transient analysis is also very important for an accurate prediction of the superconductor's behavior, but I skip this discussion by just mentioning that the time step is chosen sufficiently small in this and the following studies. The current density profile reveals how the current penetrates from the outer edges towards the middle, and the transition from the critical current density to very low current densities in the middle of the tape is considerably different in comparison to Bean model for the considered exponent. And the next question is how this evolution of the current density distribution over time translates to the AC loss. And here we have to note that local loss dissipation occurs in those regions where the current density is non-zero and the magnetic flux density distribution changes over time by inducing some electrical field. This can be seen in the figure on the left, where the penetrating flux first builds up, as well as the current density, and the loss shows the first peak at an intermediate transport current and a large change of flux density over time. In contrast, the instantaneous loss power is quite low for maximum transport current, so on this point, as the current does not change and the corresponding magnetic flux distribution in the tape section is also nearly stationary, particularly if high exponents n are considered. And here the figure shows the course of the loss power per unit length for n values of 21 and 121 as an approximation to Bean model, and you can observe some deviations in the instantaneous dissipation, whereas the average value is quite similar, as we will see in the following slides. So the solution for this problem converges quite well in JMAG 20, even though the simulation is time-consuming, but in order to assess the quality of the results, we have to compare to some kind of benchmark. And a very simple and well-established model is the analytical model that was derived by Norris. And the comparison which is discussed in the slide was essentially also made in the work from Ainley, but with another FEM software. The analytical model treats the tape in a one-dimensional approximation and yields an expression for the current per unit width of the tape at maximum current, as shown on the right here. So we have outer regions which carry the critical current density and an inner region with smaller but non-zero current density where the magnetic flux is zero. And this current density profile is shown as the blue line here in the figure on the left, where we normalize by the maximum current density. And the red and black lines represent the profiles which are obtained with JMAG for two different exponents. So we observe a quite good agreement, even though the current density clearly exceeds the critical current density in the outer regions for low n values. And in the figure on the right, you can see the current density profile for several time instants over half an electrical period and for a very high n value of 121. And here we observe how the reversal of the current density first occurs in the outermost regions, and that some numerical instabilities might arise if an artificially high exponent is chosen. However, these small fluctuations have only minor influence on the derived quantities, such as the AC loss. And the last slide I want to show before summarizing the talk is again a comparison of the current density profiles on the left and AC loss values on the right, but this time for several current loading amplitudes. These parameter studies are very efficiently done by means of the script-based implementation, requiring essentially only the execution of one master script. And on the left-hand side, you can see the current density profiles at the respective maximum current for several ratios between the current amplitude and the critical current of the tape. And we observe that even at very high current loading ratios close to unity, so here 0.99, the current density in the middle of the tape is well below the critical value, whereas the outer regions here show J values exceeding this value. And this finding can be attributed to the somewhat sluggish behavior due to the comparably low n value. The figure on the right is another comparison to the analytical model in order to validate the simulation results, but this time for the AC loss per cycle. Here we observe a quite good agreement over several orders of magnitude, which is even better in case of high N values, so here 121, as we have already seen for the current profiles. And with this, I want to end the discussion of the results and summarize the main points. We use the general interface application to export field solution data based on scripts with either MATLAB or Python, and we use this data for custom post-processing steps that are particularly needed in case of superconducting windings of rotating machines. And as shown in the second part of the talk, JMAG is also suitable to directly simulate superconductor properties with quite good accuracy in comparison with an analytical model. The specifications of the superconductor properties are again suitably done by script-based solutions. And in this talk, we looked at a very simple arrangement in favor of a clear illustration, but the generalization to more complex models, like stacks of tapes as shown on the right here, or windings in a ferromagnetic environment, are straightforward, but come along with a quite long computation time, even in case of a high degree of parallelization. And just to pick some additional aspects for the outlook, practical applications require a more advanced modeling of the superconductor's critical surface, and the simulation results for more complex arrangements must also be compared to corresponding analytical models, of course, or to the experiment. These are the main points, and now I want to thank you for your attention.
So this was the recording from Mr. Köster's presentation. Now Dr. Deusinger is still available to ask questions, and please ask your questions in Zoom in the questions and answer section or in the chat section.
Maybe I can start with a question.
Yes,
I wanted to know what is exactly the, let's say, how do I formulate this quick in a good way? Basically, the use of superconductors in machine design. So now what I've seen from your presentation is that you first use an analytical approach to sort of summarize the AC losses. How accurate is this, and can this be used actually in a manufacturing process, or would it have to be actually done with real FEA and actually have to bear with these very long calculation times? So does this analytical approach sort of replace the need for FEA?
Yeah, thank you for your question. So maybe I can share again the screen. Oh, I'm not allowed to.
Then I will try that you will be allowed to do it. So now it should work, I hope. Try again.
Second. Yeah. Yes. So now the screen should be visible.
Yes.
Yes. Yeah, you asked if is kind of accurate to use the analytical models. Yeah, and it's quite a good point, because in these analytical models you have the losses of the whole tape stack. So you have the stabilizer and whatever, and it can be used to calculate the total losses quite accurate. The second idea of the direct simulation just uses the losses in the superconductor itself. Yeah. So you have quite accurate solution here with the analytical models, but of course here this is it's a academic approach at first. So we are studying the use for the concrete application. Yeah.
Okay, thank you very much.
Okay.
And of course it's a very time efficient way to do it here.
Yeah, of course, because I'm guessing you need something with a very fine mesh, a lot of, since it doesn't converge quite easy, even if you're parallelizing it, and you have to model every strand, you're gonna have to have a very big model in the end, which needs a supercomputer to be able to calculate.
Also because of the strong non-linearity, yes.
Because you were mentioning some of the applications for aircraft, and I'm imagining for that industry, they need something that is, you cannot falter with the error. So that's why I'm asking, is it possible that this replaces this to an extent?
Yeah, it's a bit hard to say if it's such accurate for the very critical applications. But yeah, we are just already studying this. But this is an example here for the wind generator. Yeah.
Mm-hmm. Okay. Thank you very much.
Dr. Deusinger, it's Professor Tim Miller who is asking you a question in the chat. I don't know if you can see it, but anyway, I will read it.
Yes.
He writes, impressive presentation. You show a stabilizer. Is this a copper sheet in parallel with the HDS tape? If so, do you have eddy currents in this component?
Yeah, so the stabilizer is copper foil. Yeah, this is correct. And yeah, this is also addressed if you simulate the total stack in JMAG. In this slide we showed, it's maybe a bit unclear, but in this simulation also the stabilizer components are simulated but not shown here because we focused on the HTS substrate here.
Yes, thank you for the answer. Are there any other questions? Usually I wait 1 or 2 minutes, giving the participants the time to write something.
Yeah. I think it's a quite special application.
Yes.
Yeah.
Okay.
Maybe a question on the JMAG side, since you had to you basically use a script to implement some material data. I think maybe it could be useful in the future to implement this directly inside of JMAG instead of having to use a Visual Basic script to input this this material characteristics.
Yeah, because now the problem, if you manipulate the JCF file and then reopen it in the designer, then the change of material properties will be skipped again. So
Yeah,
it's not possible, and therefore we submit the JCF file directly to the scheduler, and then the designer can read the results afterwards. Yeah, this does work.
Yeah, it's a very good workaround, I would say.
Yeah.
Okay. Then okay. Then thank you. I think that there are no any more questions. So thank you very much for this presentation, for answering the questions. And let's say I will give now some final words from my side. So now I'm struggling a little bit with Zoom. Yeah, okay, it's here. So I will share my screen now. So normally you should see my screen now. It's yes, it's firstly, yes, thank you very much for the presentation, Dr. Deusinger, and also say thank you to Robin Köster, with whom you have prepared this presentation. Some final words regarding JMAG training. So if JMAG is quite new for you, then I invite you to participate at the Get Started trainings, which we will organize in November at Hannover University and at Heilbronn University of Applied Sciences. You can register for free on the PowerSys website. And if you have special requests, for example, for customized training or for coaching sessions, or if you want at least conduct a study for you or need access to a HPC cluster on which you can run JMAG, for example, then contact us. We will work out individual quotation for you. So the last point is the next presentation. It will be done by my colleague Adrien Michel from PowerSys in France. Adrien is our PSIM lead engineer, and his talk will be about optimization capabilities for a three-phase PWM rectifier. The presentation will take place at 1:15, so 15 minutes earlier than written in the program. So at 1:15 Paris time, and we are looking forward to meeting you at this presentation. But now I think it's we have a few minutes to have lunch, and yeah, since we are a French company, let's say bon appétit, and looking forward seeing you at the next presentation. Bye.